Okay, so let's look at Hamiltonians. So if I give you the Lagrangian of a system, then you can define for every generalized coordinate you have. So these are generalized coordinate. So for every generalized coordinate, you can define a momentum which is canonically conjugate to that. And it's defined by the derivative, the partial derivative of L with respect to Qi dot. And this is called the canonically conjugate momentum. Okay? So conjugate means it's married to something. What is it married to? It's married to this coordinate. Okay? And it's married canonically, married according to the law. So it's kind of weird language, but anyway, it is what it is. Let me just give. Okay. So now what we can do is that we can define a new quantity called the Hamiltonian. And the Hamiltonian is the Lagrangian minus sum over I, in case there's more than one degree of freedom, Pi Qi dot. Okay, so this is the Hamiltonian. Now let me make a comment, which is important. And the comment is that remember that the Lagrangian was a function of the generalized coordinates and their first derivatives. Can someone tell me what from this expression, what should be the Hamiltonian function of?
Qis and Pis.
Right. So Qi, because we have left Qi alone, but this is a Legendre transformation. And the Legendre transformation, what it does is that it takes this dependence and replaces it by this dependence. Okay, so this becomes a function of the coordinate and the momentum. Okay. Okay, then what happens to the Euler-Lagrange equation? So if I take the Euler-Lagrange equation, and what I do, sorry, there is no dot here. And if I plug in the expression for P, then this just becomes P dot, Pi dot. And if I plug in the expression for L in terms of H, then this becomes partial derivative of H by Qi. Right? Because H does not depend on Qi, so when you're taking the derivative with respect to H, this guy drops out, and this guy drops out, but this guy stays on, and that's why we get this thing. So this is one of the Hamilton's equation, one set of Hamilton's equation. So the other thing is that if I take the definition of the Hamiltonian and take the derivative with respect to P, then I get
minus Qi dot.
Minus Qi dot is del H by del Pi, right? This is what I get. Very good. Who is this, by the way?
Neon.
Okay. All right, so this is basically what I get, right? So these are the two sets of this two set is called Hamilton's equations of motion. Okay.
I believe there's another one if there's an explicit time dependence. Is that right?
No, there isn't. No. There's another term, and we'll come to that. I'm not sure what you mean, but when we formulate this in terms of the Poisson bracket, there will be an extra term, which is the
Size meant, I guess, when the Lagrangian will be explicitly dependent on time, then there will be another like del L del T term. So
right. There'll be another term, but not another equation, right?
Well, I guess it wouldn't provide any new information.
So yeah, let me get back to you on how I think you will see that when we talk about the probability distribution, how it changes if there's a explicit time dependence. Okay. So let's just let's keep that in mind, but you'll see that a little bit later. Okay, so the thing about there are some comments that one should make about Hamilton's equation. And the first one is that they are both first order in time derivative. Okay. And what is happening here is that we are treating the coordinates qi and the momenta pi on equal footing. They are almost symmetric, right? Except for this minus sign, it's almost symmetric. And in fact, there is some symmetry hidden in it, which there's a lot of beautiful mathematics related to that. It's a new kind of geometry which comes out of it called symplectic geometry. If any of you have done Professor Hasib's class on dynamical systems, you probably have seen some symplectic geometry. Moon, did you do dynamical systems?
Sir, I'm doing this semester.
Sorry?
Sir, I'm doing this time.
Okay. And is he covering symplectic geometry?
Sir, not yet.
Okay, not yet. Okay. All right. So this is first order in time, and Hamilton's equation is twice the number, twice as many as Euler-Lagrange equations, right? So to solve differential equations, we have to provide with boundary conditions. So the number of boundary conditions that we have to provide for Hamilton's equation are the value of coordinates and momenta, whereas the boundary conditions that we have to provide for Euler-Lagrange equations are the coordinates and the velocities. So the number of boundary conditions are the same. Okay, so